Okay. Did you drink the popcorn? Eat the root beer? You all refreshed? Ready to go? Good. Here we go. So here's our equation for waves. So of course, if I want to figure out the velocity of a wave, you multiply. Now, if we look at the unit, do a unit analysis. AP loves unit analysis. So look at this. Velocity, which we know is meters per second. We know it is. How? How is it meters per second here? Well, this is frequency. This is waves per second. And wavelength is meters. If you multiply those, you get meters per second, meters over second. A wave isn't a unit, it's a thing. So it's a thing. So a lot of times you won't see frequency written as waves per second. That's what it is. You'll see it written as 1 over seconds because it's how many per second. And a wave is not a unit, it's a thing. So it doesn't go into the unit. So if I multiply those, of course, you get meters per second. That's your velocity. All right, so there's how we get our velocity from this. We all know that we're talking about the velocity of light. So light moves wicked fast. And so it gets, that's a constant value. Light is a constant value. It has nothing to do with the Earth. Okay? No matter where you are in the universe, light's going to have this velocity to it. And that velocity is 3 times 10 to the 8th meters per second. So we use that. Call that C. C equals speed of light. So our new equation for light velocity is C is equal to frequency, I said frequency but didn't write it, frequency times wavelength. So that's our equation. It's just that we're using 3 times 10 to the 8th. Now this means that any one of these is going to be moving at that velocity. If you're a radio wave, you're moving 3 times 10 to the 8th meters per second. If you're a gamma ray, 3 times 10 to the 8th meters per second. Doesn't make any difference what kind of light you are. Of course, we can only see this one. These are all moving at that velocity. And the Earth receives radiation from the sun, and the sun spits out all of this stuff. The sun spits out all of the EMS. So we're receiving all of that. Of course, luckily, the vast majority of this gets filtered out by our atmosphere and X-rays. Ultraviolet, and we know that's not all of it does. A little bit of it does. Some of it does. But we know this gets through because we get sunburned. If you're a skier and you've ever gone to the top of a high mountain on a clear day and you hang out up there chilling like a villain, then you will get sunburned quicker. It could even be in the wintertime when the sun's not as direct because there's not as much atmosphere. If you go to the top, if you were at the top of like a 10,000-foot mountain, which you wouldn't be skiing down that, but top of a 10,000-foot mountain, you can get sunburned pretty quick, even in the wintertime, because not a lot of atmosphere, and those ultraviolets are hitting you in a much, much greater amount. All right, so thinking. Okay, energy. So the energy has something to do with the frequency. And the frequency is how many per second. So what end of the spectrum has the higher frequency? That's high energy. So it must be high frequency. Very, very good, Nick. Very good, very good. And Brady, very good. Okay, and Emma, very good too. So that means that this is high frequency stuff. This stuff down here is doing this. Where this stuff down here is doing this. Look at the frequency difference. In fact, frequency and wavelength are inverse of one another. If you have a long wavelength, you have a low frequency. High wavelength, low frequency. Right? Small wavelength, high frequency. High frequency stuff tends to get filtered out by our atmosphere. There's a lot of particles, and this stuff has a hard time getting through. So it bounces off the atmospheric particles, then loses energy. It's actually called the Compton effect. We'll go into that when we get into stuff at the end of the year. So this stuff here, why do you see the sunset as being red, orange, and yellow? Here's why. Here's your atmosphere. Those are atmospheric particles. And the red, orange, and yellow is the higher wavelength, longer wavelength, low frequency stuff in the visible light. And that can kind of snake its way through where the blues and the blues and the violets and the greens, they're higher frequencies, so they get filtered out more as the sun sets. And the sun has to go through more atmosphere when it's on the horizon. It's going through a lot more atmosphere to get to your eye. So let's draw that out for you, because it's kind of interesting, actually. So here's the Earth. Here's you on the Earth, and this is drawn to scale, by the way. And here's the atmosphere. Here's the upper limits of the atmosphere around the Earth. So don't jump. You won't be able to breathe, okay? Stay on the DL. At sunset, well, at noon, here's the sun. And it doesn't have to go through very much atmosphere to get to your face, does it? Okay, so the blues get a little bit scattered, because remember, that's the high frequency and a little bit scattered, and that's why you see the sky's blue. But in the evening or the morning, here's the sun. There he is, Mr. Golden Sun. And the sun rays have to go, actually they get refracted, so I'm going to draw that in. I haven't talked about that yet, but that they get refracted, and they get to your eye. But look at this. They have to go through all of this atmosphere, where at noon, they don't have to go through very much atmosphere. So all this atmosphere is going to definitely filter out all the blues, definitely going to filter out the greens. Some of the yellows can get through, but the reds are going to be predominant, the only ones that can kind of get through, and even they get scattered a little bit. So it's kind of an interesting application of why the sunset is, or the sunrise, is red, orange, or yellow. Okay, and actually the more crap that's in the atmosphere, the more pollution that's in the atmosphere, that actually gives you nice, big, brilliant red sunsets. Makes it pretty. Well, let's put crap in the atmosphere so we can have better sunsets. All right, okay. We got to talk about a few more things about light, the general aspects of it. I made a list so I didn't forget anything. Talked about that. Okay, and light changing fields in the inverse square law. When it comes to light, and most things in physics, there is an application of something called the inverse square law. This applies to all forces, inverse square. Inverse square is this. What does it mean? What is inverse square law? That means r is distance. So it's a relationship squared, because life isn't in 2 dimensions, it's in 3 dimensions. So if you move something, like with gravity, if you move something twice as far away, the gravity goes down, inverse goes down, inverse, greater distance, inverse goes down by 1/4 inverse square. So if I double the distance of something, gravity is 1/4. That happens with all forces. And it happens with light, brightness, or intensity. So when it comes to light and how bright and intense light is, intensity is an inverse square. So if you have your 100-watt light bulb on over here, and I'm a meter away, we can measure light intensity. We actually have light meters that we can measure light intensity. If I go to 2 meters away, hey, the amount of luminosity, the amount of lumens, went down to 1/4, because I doubled the distance, invert that, double the distance, invert it, 1/2, square it, 1/4. So it's an inverse square relationship. So very quickly, if you've got a light and you just move twice as far or 3 times as far, it's 1/9 the amount of intensity. Very quickly, the amount of intensity of light goes down. Inverse square law. Remember that. It applies to everything in physics. One of the cool thing here about light is now we're doing light before electricity and before magnetism. Electromagnetic. So we're doing light before this. It's okay, sometimes I do that, and in some physics books will be set up that way. But sometimes light is done after electro and magnetism for this one reason. And it's only this one reason, so that's why I decided to put it first and do it first. I like doing light and getting light and optics out of the way first. I don't mean out of the way. I think it's awesome. But electromagnetic, light is both electricity and magnetic properties to it. And those properties are at right angles to each other. And what happens is, is that light is divided into an electric field and a magnetic field, which are at right angles to each other. There's a picture in the book. I'm not good at drawing right angles. Things that, terrible. Trying to draw 3 dimensions on 2 dimensions, forget it. I can barely draw stick people. But what happens is, what you'll see is, sometimes you'll see a picture of light, and you'll see a field. Well, I'm going to try. And you'll see a field. Arrows represent a field. They represent field lines. And and this bubble here might represent the electric field. And there's a magnetic field that it's not up here. It's like coming out at you. How am I going to draw that? And it's coming out at you. See, I'm terrible. I mean, it wasn't totally terrible, but the 2 fields are at right angles to each other. And we'll talk a little bit about more of what that means later on. But the electromagnetic spectrum, a wave of light, the light waves actually have 2 waves to them. One is an electrical wave, and one's a magnetic wave. So there's an interchange between electricity and magnetism going on. Light's weird. It's really cool. And we get into a lot more of light and stuff when we get into the last unit of the year, which is quantum mechanics. But I think that's going to wrap this up. It's already 11 minutes, and we've covered now the basics of what we need to do to introduce light to you. All right, and I will be making some videos on what's called Snell's law and reflection. But for now, TTFN.